Well, thank you for inviting me to be the UK counterpart of Long. Well, actually, I'm French UK now. I'm in both institutions, but I'll try to speak about the English landscape. So it's the first time I give such an exercise. I make such an exercise, so I'm not sure I make a good job out of it. And I'm so grateful of being after Long, because a lot of the notions it has defined, I'll be just briefly going through to explain what we do from them. So this is going to be a quick roadmap on statistics in the UK. So, I mean, as Long might have shown you, statistics is quite diverse. And so I'm not going to talk about every kind of statistic that's done in the UK, because that's like an endless game. I'll be concentrating a bit in different aspects, and then finishing by a stronger concentration on the kind of domain I'm working in, because I know it better. I start with the statistical machine learning. So this is a lot about what Long was talking about, generative models, deep neural networks, all that sort of thing. That's called like statistical machine learning, and it's mainly around prediction. Then I'll talk about computational statistics, so which is like how hard it is to implement the algorithms that we're considering, what are the challenges and what are the questions, and what kind of research is done in the UK in this regard. And I'll move to Bayesian statistics, which is very important in the UK because of figures like Lindley and Adrian Smith, who were like instrumental in developing the field. And I'll end up with a bit of on causal inference. That was sort of the open question Long was talking about. So first of all, statistics, where do you find it in the UK? So you typically find it in statistics or mathematics departments. Sometimes they are joined, sometimes they are separated. You can also find it in around machine learning. So then machine learning, you find it in all sorts of departments. You find it in computer science, engineering, and statistics and mathematics. You also find statistics in biostatistics, which is much more applied, but that sort of gets the same questions. So this is very wide, and I'm going to focus on, as I said, Bayesian computational statistical machine learning and causal inference. So first, statistical machine learning. So I mean, this is a growing field. This is super fashionable. That's what people now call. They used to be machine learning, called machine learning, and it was super big. And now it's AI, and it's super big. It's even bigger. But it's all the same continuation of the same thing in a sense. And there is a strong connection between statistics and machine learning. And in the UK, there's a strong connection between statistics done, machine learning done in the academia, and machine learning done in industry, by people having joint appointments between industry and academia. A lot of the PhD funding is done with industry funding. A lot of students go to industry. So one way to try to have it keep it moving while keep having students is to have students do a PhD, students and master do a PhD and then go to industry. So have a PhD oriented, which are more machine learning and applied or methodological. So I give a few examples of people who are, for instance, who have this double affiliation between industry, mind typically, and in academy. And because it has such a wide or diverse sort of landscape in the machine learning in the UK, but actually everywhere in the world, you have it's also very diverse in the way the research is conducted. So you have applications, and you have methodologies, and you have theory. Okay, and so just to skip about to talk about the kind of methodology, I'll just write now. Methodologies or tools that are used in machine learning. Some have been developed or very promoted here in Edinburgh. Gaussian processes. They are used very much in machine learning. They are very much used in statistics, and sort of the continuation to Gaussian processes are kernel methods. So this is a big area in machine learning. And it corresponds to trying to represent function as object in a reproducing kernel hyperspace. Deep learning that Long was talking about. So this is a sort of a big area now over the last 10 years. It's been like getting bigger because it's proved so efficient, even though people don't really understand how it works and really why it works so well. So there are lots of people working at the intersection between mathematics, physics, and statistics and computer science, trying to figure out what's going on there, and it's not quite clear yet. Generative models, so they use deep learning as Long was talking about. So the idea is to try to not only try to understand what's the distribution that's underlying your data, but more generate data, new data that looks like the previous one, but that's a bit different. And that's and deep learning here is a key process. And after the generative model are these large language models, which are ChatGPT. Another aspect of machine learning that's very important, and for which you can find some researcher here in Oxford in particular, but not only, is reinforcement learning. So you have theoreticians and methodologists. So like in Cambridge, you have Mihaela van der Schaar, and in Oxford you have, for instance, Patrick Repeschini. And the last one is Bayesian learning. So Bayesian learning is trying to figure out uncertainty quantification using Bayesian tools on these high dimensional or super high dimensional models that are deep learning models, for instance. So and that's not to speak about other things. So machine learning, it started to be prediction. And then people realize that not only do they need to predict, but they need to be able to interpret the results. And now they call it interpretable machine learning, which is a bit like statistics, because that's the point of statistics, is trying to be able to interpret the parameters or what's going on in the generative model. So that's we sort of looping towards statistics to machine learning to back to statistics again. Privacy, this is a big thing, and it's trying to make the data anonymous. And then, of course, when you make the data anonymous, one way to do it is to add some noise, and then you want to understand how it's going to be affecting the inference that you'll make on this noisy data, and how can you sort of try to find a trade-off between being private and being precise. And one of the modern aspects of it is that a lot of the data are in small units, telephones and things like that, and you want to make inferences using all these small units, but without the units communicating to one another. And this is called federated learning and distributed learning. And it creates a lot of challenges in terms of computation, but also understanding how to make reliable, robust, efficient inference while not communicating to one another too much. So these are like really very active research areas in the UK, in all these places I mentioned, and I'm probably forgotten some. So as I said, one of the key problems here is like computation, because you're working with big models, and so you want them to be scalable. So this is what Long was talking about. So in computational statistics, you have two types of approaches: optimization and sampling. Optimization is more frequentist and machine learning now, and sampling was more like towards Bayesian methods, but they don't have to be. Yeah? So optimization, what does it mean? It means that you have this function f, and you want to find theta that minimizes or optimizes the function f, or maximizes the function f over some space, capital theta. So why is it important in machine learning and statistics? Is because typically what you're interested in is trying to minimize some risk. Okay, so you don't have access to the risk, which is an expectation with respect to the generating data of some loss. What you have access to is empirical risk. So these are some here. So the yi's are the data. You assume that they come from some model which you don't know. You compute a loss function, so which sort of measures what you lose when you observe y and when you propose theta as a generating mode parameter. And it's empirical risk because somehow this sum here corresponds to the expectation with respect to the empirical measure, which is the sum over the point masses on the observations. And typically, because you're working in high dimensional setups, you add some penalty, which can be whatever it is. It's a penalty in terms of how complex the data, the parameter is, smoothness, sparsity, blah, blah, blah. And the aim of the game is to minimize these functions. And this is the key, one of the key steps when you do a frequentist estimation or machine learning optimization for deep neural network, for instance. This theta could be all the parameters in your deep neural net. So these functions typically are not necessarily convex. They are typically non-convex. And so the question is so you have a theoretical question that say, can you get some guarantees on the kind of convergence that you get and to what? And other questions are, how can you make it efficient and scalable? How can you make it distributed? How can you make this optimization distributed on different units? So you have all these sort of methodological and theoretical questions, and they are answered by people who use them and by people who want to study them. And these are done in different departments in the UK. Sampling methods were more Bayesian because, as Long was talking about, in the Bayesian statistics, you have a whole distribution, and I'll come back to it later on. You have a whole distribution on the parameters, which is the posterior distribution, which is the basis of the inference. The inference in Bayesian statistics is based on this distribution, and you want to sample from it. You don't want to compute one point estimator, but you want to sample from it. And when the theta is huge, is a big complex or lives in a complex space, like a manifold or something like that, then sampling is complicated. And so you need to come up with an algorithm that scales well to the dimension, the number of observations. And so this is a big field, and it has been a big field in the UK for 30 years, essentially. It's still a big field, despite the fact that people say, well, sampling like these MCMC algorithms, which are Markov chain that you construct on the space, and which target there are reversible Markov chain that target the distribution you want to sample from. These algorithms, they don't scale well with the dimension. And so what you try to do is to sort of combine ideas of sampling like that with optimization to make it more scalable. And so this is the new trend, trying to devise algorithms that combine optimization and sampling. But still, a lot of questions are of interest for people working, for instance, in Bristol or Warwick, and a bit in Oxford as well, and Imperial, which is how can you make these algorithms or some versions of these algorithms scale well with the dimension or the geometry of the space. If you are in a constrained space and some weird things can happen and you're not mixing, the Markov chain that you're considering is not mixing well, and so your algorithm becomes less reliable. So there are all sorts of the questions there, and that have been the topics of research for many years in the UK and are still very lively. And as I was saying, now people try to combine optimization and sampling to come up with distribution. So because when you have a distribution, it's much more rich as information compared to just a point estimator, which is a minimizer of a loss function. But of course, it's much more complex to obtain because you want something bigger. It's a distribution and not a point. And so one way to do that is to do approximate methods. So you're not going to target pi exactly. You're going to target something a bit different, which is called which you define. So you choose a set of possible distributions that you can sample from. And among these possible, so script Q here, among these possible distribution on theta, you're going to choose the one that's a minimizer of the Kullback-Leibler divergence between Q and pi. So that's called the variational Bayes method. And then so this has the advantage that it's supposed to be not too far from pi, or hopefully. And when you sample from it, you can sample from it. So that's an advantage. Of course, it has lots of questions because it's supposed to be not too far, but you don't know. So it can be quite different. So, and in particular, it gives you, so how bad are you? So how close are you to pi? That's one of kind of questions that have been trying to be investigated. And another type of question, which is something that with people in my group and in other groups like in Imperial, people have been looking at is, even if you're not close to pi, what are the statistical properties of the output of your algorithms? Okay, that's so that are the sort of key ideas. There are lots of other possibilities for trying to combine optimization and sampling. But this one is one of the most famous, and it's something that has become much more popular after in the Bayesian deep learning community, when people have used variational autoencoders and Bayesian deep learning. That's the kind of method that they use, because they cannot directly sample from the posterior distribution. So now I've been talking about posterior distribution. Long has been talking about what it is, but I'm going to define it more precisely. So I'm going to describe what Bayesian statistics is about. So you have some data Y, and as Long was saying, this data Y can be very different. You can have graphs, it can be data, you can have images, you can have ID observations from something simple, or you can have ID observations that are on a manifold. It can be anything. And so in statistics, typically you consider that this data is random, and you imagine that there is a probabilistic model P theta, where theta represents what you don't know in the probabilistic model, but it can be very different depending on the models that you're considering. And so theta is what you don't know in your generative model. So it's called the parameter. And in the Bayesian approach, you're going to say, well, I don't know theta, so I'm going to represent it as a random object as well. So I'm going to construct a probability distribution, pi, on theta. And that's called the prior probability distribution, because you do it before you have observed the data. So it's done a priori. And then using Bayes formula, so it comes from Bayes, then you update your knowledge by looking at the posterior distribution, which is a conditional distribution of theta given y, which is proportional to the sampling model P theta times pi of theta. Okay, so that's your object of interest. When you do in Bayesian statistics, that's the whole thing that you're interested in, because it gives you point estimators like the posterior mean, credible regions, which are regions for which you have a high posterior probabilities, so measures of uncertainty and point estimators. But then, so now a lot of the interest in the modern statistics are looking at high-dimensional models, non-parametrics and semi-parametrics. So non-parametrics means that theta are functions or sets of functions. So you're working in an infinite dimensional space, but it's infinite but structured. So in a sense, it's simpler than high-dimensional. High-dimensional is it's not necessarily infinite dimensional, but it has a lot of parameters. Typically, the number of parameters is larger than n. Like for instance, to give two examples that Long was talking about, the regression example, f is a function here, and you don't say anything, so it's an infinite dimensional model. But to some extent, it's easier than this high-dimensional problem where beta is just a parameter in our P, but P is larger than n. And it's easier because there is no structure on beta, whereas on F, it's a function, so you can assume that it's smooth, and then you give some structure, and then the dimension becomes, all of a sudden, the effective dimension is smaller. And semi-parametric inference is something in between, where you have this high-dimensional or infinite-dimensional parameter space, but you're interested in something low, like just a summary of your parameter, maybe one of the parameters, or something like that. And then in this case, it's called it's a low-dimensional object of interest. It's been a topic for a long time in statistics, but there is a revival of interest here because of causal inference, because it's very, very important in causal inference. So you have the key challenges. The three challenges are modeling, how to model P theta pi. So there are two different types of models. How to model then computation, which I've already talked about, and understanding the theoretical properties. So for modeling, just to give you an illustration, so I've listed people. So a lot of people, because Bayesian statistics is very important in the UK, you find people working on the modeling aspects in a lot of places. I've listed some important ones, but there are others upstairs. And so just an example, imagine that your data is a network. So I've plotted a network, and you want to construct generative models for this network. Okay, so there are models that exist in the literature, like R2 Shreni graph or some, I've forgotten the name, but it doesn't matter. But they are limited because they are dense graphs. If you want to have a sparse graph, then it's more complicated. And how can you construct a probabilistic model for sparse graphs? So that there has been quite a lot of research in the UK there, in particular in Oxford, because François Caron was one of the leaders in this field. But then there are people in Bristol and UCL. Bristol is for more like the frequented graphs, and LSE and UC and to sample that. So you want to understand these models. So you want to understand what's the probabilistic model that you're considering here. So it's more understanding pi, the prior, and how do you construct a model on such an object. Another example is simpler to understand in a sense. So you have this regression model of y equals f of x plus epsilon, for instance. But you want to construct a prior on f when f lives on an x, which is very weird. So for instance, it's a manifold. So how can you construct a function that lives on a manifold? And you want to construct a distribution on functions that live on a manifold, keeping as much as you can in your way of your constructing your distribution, the geometry of the manifold. So that it's sort of clever. So there is there have been in the machine learning community, so it's between Bayesian and machine learning, a lot of research on trying to understand how to construct such an object, like using Gaussian processes, for instance. So that I've talked about. Now I want to talk about the mathematical aspects. And so one of the reasons why I want to talk about it is I want to have you sort of understand that now with the machine learning and statistics and the sort of modern statistics, let's call it that way, there are more and more connections between statistics and or machine learning and different types of math. And somehow this is one way of one aspect where you have them, like optimization was another one. And it can maybe be important for people who are not a statistician, but who do different types of math, but they can connect to statistics because of these questions that people ask. So the kind of statistical properties that you are interested in when you're looking at the posterior distribution is, if I increase the number of observations, am I going to learn what I want to learn? And so how do you say that? What you're saying is that, is my posterior distribution on theta, is it going to concentrate towards the point parameter I'm looking for? So the one I'm supposing that there is a generative model, am I going to concentrate on this generative model? And am I going to learn what it is? It's called posterior contraction rates. So in other words, you want to learn at which rate your posterior is going to concentrate near theta naught if you assume that there is a true theta naught in your generative model. So you're looking at a Bayesian object, which is a posterior distribution, but you're taking a frequentist way of thinking about it because you're assuming that there is a true theta naught. So and as Long was saying, and it's exactly true also as well in the UK. There is this theory is it dates from the 20 years ago in a sense. So but now the big question is, how do you handle complex models? Networks is the one I was talking about. Point processes or diffusions or SDEs that are like Long was talking about. Another big one, which is related to PDE, and I've seen that there were quite a lot of people talking about working on PDE here, are inverse problems that are defined through PDEs. And you want to learn the parameters of your PDE, and the parameters are functions. And then in this case, you have to combine applied mathematicians who work on PDEs to statisticians who can study the statistical properties of the algorithm that you're going to use to estimate the parameters of your PDE. And so, one of the key persons in the UK who has been doing this connection is Richard Nicol in Cambridge. Another important class of problems that are related to that is this loss function. The choice, it depends very much on the choice of this loss function, because in infinite dimensional models, the metrics are not equivalent, and then all the properties differ depending on the loss function. And so that's the first class of problem, and somehow, even though it's not simple, it's not the complicated, it's not the most complicated one. The most complicated one is trying to understand the uncertainty quantification, which is crucial if you do statistics. Statistics is all based about giving an estimator and validating your estimator, giving some error measures, error bounds on your estimator, because otherwise you're not saying anything. If you say, well, okay, the probability is 0.5, But if it's 0.5 plus or minus 0.1, it's fine. If 0.5 plus or minus 0.5, it's 0. I mean, you don't learn anything. Yeah? And so this is what you want to know. And so, and the Bayesian version is looking at credible regions. So set C, such that the posterior distribution on being C, it's a posterior on theta, is fixed, is like high, let's say. So this you can compute from the posterior distribution. This is something that's easy to compute to some extent if you can do the computation. The difficult part is verifying that this guy, I forgot that, has also good frequency property. So somehow you're robust to the choice of the prior. That's what it means. And this and trying to figure out what's the uncertainty that you're doing when you're considering a Bayesian method. This is a difficult issue. There is a lot of research there. And there is a lot of research to be done, and some people are working on it, as written here in the slide. And then recently there have been some excitation, which I think is quite exciting actually, and trying to combine the asymptotics on the posterior distribution with complexity estimation on the algorithms, and trying to figure out whether the asymptotics that you know on the behavior of your posterior distribution can help to understand whether your algorithm is going to be efficient or not, and what's the impact of the dimension and that sort of things. I mean, as I said, I was going to talk briefly, but for the interest of time, it's going to be very brief. But that's my last slide on causality. So causality, it's an old topic, but it's been like essentially dormant for like tens of years, and now because of all the medical applications, it's becoming more and more important, and there is more and more research about it. You've heard about it during the COVID. What is it? What is causality? Causality is you want to understand what will be the next effect of a given cause, let's say. That's one question. The second is which cause has caused that effect? And there are two different questions, but they look very much alike. An example is that you have some response Y, let's say whether the time to death or the time to recovery, and you have some covariates X, the blood pressure, the age, the sex, and blah, 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 and you have a treatment. And what you want to understand is whether the treatment is efficient or not. If you have a random clinical trial, you can answer this question. But if you only base yourself on observational observations, like people, you see some doctors have given some treatment, and then you see whether the patient has recovered or not, there are lots of biases that come in. And the biases come from the fact that in these observational studies, the treatment allocation depends on X. And so when you want to study the effect of T, you cannot disentangle it from the effect of X. And you have to be able to do that, you need to some further assumption of conditional independence. And so a lot of this research has been driven by graphical models, DAGs, by people like Stefan Lauritsen, who was in the UK at the time, now he's back to Copenhagen. And that's also related to a missing data problem and potential outcome framework. And so there are lots of research that are in between game theory, probability, and statistics on this notion of causality. Thank you.